So if you recall, when we originally were looking at creating tables for databases, we had a table and we had a first name, a last name, and a phone number column. And we said, okay, that's great, but what if somebody had multiple phone numbers? Should we add more columns for, home phone, cell phone, work phone, blah, 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 and so on? Or should we just add multiple rows when a person has multiple phone numbers? And we said, there were trade-offs between the two. So we considered breaking the data into multiple tables, and this process is called normalizing your data. So what we're going to talk about is we're going to talk about what is famously known as the first normal form, the second normal form, the third normal form, and then finally the Boyce-Codd normal form. And these normal forms go in progressive order. So in other words, we're going to place restrictions on the functional dependencies of our data, of our tables. And we say must follow the following restrictions. And if it follows a certain restriction, it's considered first normal form. And then these get progressively stricter. So the second normal form follows first normal form plus maybe has an additional restriction. And the third normal form follows the second normal form plus has additional restrictions. And same true for the Boyce-Codd normal form. So the idea of normalizing data is basically we're going to decide how to organize our data, cut it up into tables, have the tables interrelated to each other by using foreign keys, or columns that have data that is in common if we want to do a one by many or a many by many relationship. The idea of normalizing data, a lot of the credit goes to two famous computer scientists, both worked at IBM in the database field. And their names are Boyce and Codd. Boyce is very famous for being one of the co-developers of the SQL language, which is the language we interact with the database in. And also, he was a researcher in relational databases. Codd was famous for developing the idea of the relational database model, which is where you have tables with columns, and then the tables are interlinked with each other by having data in some of the columns be connected to foreign keys in another column, and so on. And Codd is probably still most famously known for the normal forms of data. So before we go over the normal forms, maybe it'd just be a good time to do a little refresher on topics we've talked about in the past. So for example, the data domain of a value refers to the type of data that a field can hold. So for example, if you have a phone number could be 10 digits or whatever the definition is for that field. Could be varchar, and then the question is what possible range of numbers can go into those fields. How many fields can go in. An atomic value is a value that cannot be decomposed into smaller pieces. So for example, we couldn't say that a person has two phone numbers because we could say, well, one phone number is for one phone and another phone number is for another phone. So that's what an atomic value is. And then just a reminder, when we talked about functional dependencies, a transitive dependency is a dependency where if you have a set of columns, that if you knew the values for a record in those columns, you could positively identify the columns in a second field, and if you knew those values, you could positively identify the third set of columns. So if X can tell you the value of Y and Y can tell you the value of Z, then there is a transitive dependency from X to Z. If you're given the value of X, you could positively identify the values of Z. You would do it in two steps. With X, you would figure out what Y is, and then with Y, you could figure out what Z is. Okay, now for a database, if it has columns in it, if you have a set of rows, let's say you have 8 rows, A through H, and I came along and I told you that if you know the value of fields A, B, C, and D for any tuple, any record in the database, then you would exactly know the values of the remaining fields, E, F, G, and H. So if I give you the values for A, B, C, and D column, you can positively tell me without a mistake the remaining fields. Then those columns, A, B, C, and D, would be considered a super key for the database. If you knew those fields, you could tell all the other remaining fields for all records. It is possible that there could be overkill. Maybe I'm telling you the values of A, B, C, and D, and the truth of the matter is you only need A, B, and C. You don't really need D. If you knew A, B, and C, you could figure out what D is. Plus you could figure out E, F, G, and H. So the collection in that example, A, B, C, and D, would be considered a super key of the set. I give you A, B, C, and D, you can tell me everything else. If it turns out you don't really need D, the only 3 fields you really need are A, B, and C, then A, B, and C would also be a super key, but it would be a special kind of super key in that it's a minimal super key. All the fields are needed to be able to tell all the remaining fields in the database. So a candidate key is a minimal super key. There's no fields in that that are unnecessary. They're all necessary. A super key could contain unnecessary fields. And then a non-prime attribute in a relationship is an attribute that does not belong to any candidate key in the relationship. In other words, its value is determined by other fields. It does not in any way, is not in any way needed to determine any other value. So we call that a non-prime attribute. Okay, so the first normal form, which gets accredited to Codd, I think this was around 1971, the first normal form is if the domain of all the attributes contains only atomic values. Okay, and then the value of each attribute contains only a single value in its domain. So, for example, this table would not be considered in first normal form because a person could have multiple phone numbers. So, for example, if a person was to get a second phone number, for example, in this case, Jennifer got a second phone number, we'd have to put 2 phone numbers here. And then the idea is that this would not be an atomic field because this could be broken down into phone number 1 and phone number 2. So this field is not atomic. So the way it was defined is not atomic, and therefore this table could not have a field that could only take on one value. We could design the table in such a way that every time someone gets a new phone number, we create a brand new record for that person. So we would have the ID telling us who the person is, who the first name is, who the last name is. And then they could have one phone number. And then a second record, same ID, same first name, same last name, with a different phone number. This table could now be considered in first normal form, and the reason is that the candidate key for this table would now be both the ID, let's say the ID could tell us who the first name and the last name is. Now the ID and the phone number can uniquely identify who the person is. Thank you. So, okay. So we would have to add this, we'd have to add the idea that every time a new phone number comes in, we'd have to repeat the first name and the last name. And we'd also now have the ID and the phone number together would end up being a candidate, a candidate key for the table. Another way of doing this, which could be argued, I think the first day of class we argued this would be a better way to do it, would be to have the IDs tell you who the first name and the last name is, have that be in a separate table, And then as people add phone numbers, just, add phone numbers. So now this person 456, which is this person, has 2 phones. And now we're across 2 different tables. So in this table, this field, the ID is the key for the first and second candidate key. If you know who the ID is, I can tell you who the first name and the second name is. And if you know the ID, I can tell you the phone number, but because, I'm sorry, that's not true. If I know the ID, I can't tell you the phone number. So the phone number and the ID jointly together are the candidate key for this table. But this table is now in first normal form because a person can't take on multiple first names and multiple last names. A person can take on multiple phone numbers, but they will be on different records in the database. So we don't have any field that could take on multiple values. Every field is atomic. So then it would be in first normal form. In order to be in second normal form, and like I say, this is progressive. In order to be in second normal form, you have to be in first normal form plus meet an additional condition. So the additional condition would be, first of all, we have to be in first normal form, and then no non-prime attribute, which we said is an attribute that doesn't contribute to any candidate key. No non-prime attribute can be a proper subset of any candidate key in the table. So suppose we had a database, a table, that went something like this. We have a person, and the person does a task. This is from that show Jersey Shore. So you have a person, the person does a task, and then the person has a town that they live in. So in this table, the person and the task together become the candidate key for the table. But the person alone, which is a component of the candidate key, the person alone can tell you where the person lives. So in other words, I don't need to know that they're going to the gym to figure out where they live. That would not be necessary. So this column, which is not part of can consider it part of a super key, but it's not a candidate key. This column and this column together are the candidate keys. But this column is determined by one of the fields of the candidate key. So in order to be in second normal form, no non-prime attribute, like where the person lives, can be dependent on a proper subset of a candidate key. So this is the candidate key, these two together, but this field is only dependent on one of them. So that makes this in violation of second normal form. It's in first normal form because a person can't live in multiple towns. Tasks are broken out separately, so the same person can do 3 separate tasks. That's allowed. So we're not going to put multiple tasks into one box. So it's in first normal form, but it's not in second normal form. The way we can push this into second normal form is to split the table again. We can have the people and the tasks, and then this would be a candidate key. Both columns would be a candidate key for this table. And then we could say the people, the person, and the place where they live. So this field, person, would be the key for where they live. So this is a second normal form version of it. And this is it's a pretty important concept, the second normal form. So this is where you start putting in data. And you might not even think about it. I do this a lot of times where I start putting in columns, and I have columns dependent on a subset of the columns in my table, and this could end up being a problem when you start doing SQL statements and you do joins that are not natural joins of the tables, and where you're looking for fields that match in names. You could end up generating records that were not intended for your database. So here's just another example of being in second normal form. So suppose we had a table that had a season 1, season 2, season 3, season 4, season 5. And then maybe some people vote on or enter a number for what they believe is the best episode of that season. So if you took a season plus an episode number of that season, so these would be actors in a TV show. So this season, this episode would determine who the main actor was of that episode. And then we have another column, which is the date that the final episode was aired. Now in this case, the season and the episode would tell you who the main actor of this season, that episode was. So this would be the candidate key, season and best episode would be the candidate key. But this field, what day the last episode aired, is only dependent on the season. So again, that's a violation of second normal form. We have a field, a non-prime field, that is not dependent on the entire candidate key. It's dependent on a subset of the candidate key, just one field in the candidate key. So the candidate key is season and best episode, but it's not in the second normal form because the season can tell you the finale date, the final episode, the final episode was aired. So this is not in second normal form. And what do? We cut it into smaller tables. So that's how we put things into normal form, keep breaking it up into smaller tables. So what we can now do is we can say something like this, and maybe different people will put in different numbers, and that'll generate a different field here. But we can have season 1, 2, 3, 4, 5, and then maybe whatever people think the best episode is. So if you looked up that season and that episode, you get the actor or actress that was the main actor for that episode. And then, so now the candidate key for this table is season and best episode, which tells you this value. And in this table, the season is the candidate key and tells you the date of the finale. So the idea is we want to put this connection in a separate table. And one of the issues is we would be susceptible to putting in, someone could add a record, let's say season 4 with a different episode, and we have who the candidate, who the best actor or actress is. But we could actually put in a wrong date for the finale. So not only would we have redundant data, the door is open that we could have wrong data. Because there would be nothing that said, if I put in a new record, season 4, episode 5, with a different main actor, and then had the finale date and I typed it in wrong, I now have two different seasons. I'm sorry, I have the same season having two different dates for its finale, and now definitely my date is wrong. And there was no way to prevent that from going in. You're just hoping people are entering records correctly. Okay. So by breaking it into two tables, forces us to only have one answer to the question, what date was the season 4 finale aired? And we only get one answer, so it's either 100% wrong or 100% right. Instead of having multiple answers, which means at least one is wrong, possibly they're all wrong. Okay, so now the question becomes, since the second normal form is a more restrictive version than the first normal form, not only is every field can only have one value to it, but we also removed the fact that we could have one part of the candidate key. The candidate key is both of these fields, but one part of it, or a subset of it, a proper subset of it, can tell you the value of another column. Okay. So, the second normal form is a more restricted version of the first normal form. So if we put our tables into second normal form, it's a little bit more difficult for us. We probably have to, we'd be changing our SQL statements to be writing, when we add a new record, we would have to add it into two tables. So this will impact our stored procedures. But the other thing is that there would be an advantage of it when we start doing SQL statements where we're looking for records that match. Let me go back a second. If we were to look for records that, if we compared this table against another table saying, you know, where season equals this and episode equals this, and then they have a season and an episode column 2, we would then take a record here and line it up with a record that they have. The idea that we would be bringing in this date on one scenario and possibly bringing in a different date on another scenario, we could actually then start generating records where season 1's finale date is one date and season 1's finale date is a different date, and now we're making 2 sets of records in those. So we'd like to avoid that, and it would be in our best interest to try to adhere to these normal forms. So the third normal form is a restriction on, again, normal forms are based on restrictions on our functional dependencies. So to be in third normal form, a relation has to be in second normal form, which means it has to be in first normal form. So it has to be in second normal form. And then in addition to that, every non-prime attribute is non-transitively dependent on every superkey. Okay, now that said another way is basically saying that if you have, in any of your tables, if you have a dependency where x, knowing the values of x will tell you what the values of a is, then at least one of the following is true. So x either completely contains a, that is that, you know, it's a trivial dependency. So an example of a trivial dependency is suppose you had a table that had a person's first name and a last name. And I said, if I tell you the person's first name and last name, can you tell me their last name? Well, yeah, you'd look at the last name and tell me what it is. So first name and last name can tell you what the last name is. First name and last name can tell you what the first name is. So that's a trivial dependency. If this set of fields gives you this set of fields, if this set of fields is just a subset of this, that's just a trivial dependency. So you're in the third normal form if a functional dependency gives you a set of values, if x contains a, that's the trivial version, or x is a superkey to the relation, meaning x tells you everything, not just tells you some things. And the other condition would be every element that is not in the set x, a minus x, all the fields that are not a, that are in a but not in x, which is the set difference between a and x, is a prime attribute. So in other words, each attribute in a minus x is contained in some candidate key. So 2 different ways of stating it, but I think it's probably easy to follow with an example. So if we have this example again, where now it's almost the same table as we looked at last time. We have a season, we have an episode, what someone adding records is saying what they think is the best episode. So again, in this table, someone could say, for this season, I think something else is the best episode. That would generate a different best main actor. But in this case, the season and the best episode will tell us who the main actor is. And then we have that actor's date of birth. Okay, so in this table, the candidate key is again season and episode. You give me a season, you give me an episode. I can then tell you exactly who the main actor is for that season, that episode. And then once I know who the main actor is, I can tell you that actor's birthday. So this field is dependent on this field. And this field is dependent on these 2 fields together. since actor tells us date of birth, then this is not in third normal form. So the way to turn it into third normal form would be to turn it into two tables. One table telling us the season and the episode. The season and the episode will tell us the main actor. And then the actor has a date of birth. So does this seem the same as the last example, or is there a difference between the last example and this example? So the difference is basically this. In this case, we had season and episode would tell us who the actor is, and then season could tell us this last column, season, which is a subset of the key. So that was the violation, that it's not in second normal form, because this field could tell us this field alone. Okay. In this case, third normal form is every non-prime key, which would be like the date of birth, is non-transitively dependent on the super key. It can't be transitively dependent on it. So, the super key is these two fields. These two fields tell us the person tells us the date of birth. So this field is transitively dependent on the super key. So that makes this not in third normal form. It is in second normal form because there is no field, there is no column that is dependent on part of the key. It's not like season tells us the date of birth of a certain actor, or that best episode will tell us the date of birth. And these fields alone will never tell us who the best actor is. So this is the third normal form of that example. So what we're basically doing is, again, and we're almost always going to solve by putting into a more restricted version, is to take the table and split it. And split it and have something hold them in common. So the first season with this episode tells you who the main actor was, and then the actor has a date of birth. And once again, we can't have multiple dates of birth for a particular actor. We have multiple entries here. We would never have a multiple date of birth for the actors. And then the last version of, I guess the most restricted version of Boyce-Codd, is going to be called the Boyce-Codd normal form. And this is a version where all redundancies based on functional dependencies have been removed, although other types of redundancies may still exist. The relational schema R is in Boyce-Codd normal form, if and only if, for every dependency where X gives you Y, at least one of the following conditions holds. X gives you Y is a trivial dependency like we had before with third normal form. So Y is just a subset of the fields in X. Or X is a super key of the entire relationship. So if X tells you anything, Boyce-Codd normal form kind of summed up in one sentence is, if X can tell you any particular field, then X can tell you everything. X should not be able to tell you some data and not other data. So, for example, suppose we had a collection of students taking courses, and then the student taking that course has a certain teacher for the course. So, Jennifer Farley taking operating systems has the teacher Clayton. Okay, Nicole takes databases, teacher's Byrne. Jennifer takes databases, teaches Burn. And then this student, Michael, takes operating systems and databases, and has the teacher, Clayton, and the teacher, Wang. Okay, now, suppose this is at a university where every teacher can only teach one subject. So what that means is that this teacher, Clayton, only teaches operating systems. And here he is again, operating systems. This teacher, Byrne, only teaches databases, and this teacher, Wang, also only teaches databases. So a teacher cannot teach multiple courses. Suppose that was a rule at this university. So, in this case, the combination of student and course could tell you who the teacher is. See now, for example, this student taking database has one teacher, but this student taking the same course has a different teacher. So you need to know the student and the course. And we have a rule that says the same student can't take the same course with two different teachers. So in this case, the student and the course together can tell you who the teacher is. And because this university has a rule that every teacher can only teach one course, the teacher can tell you the course. If you know the teacher, you know the course. So this is in third normal form because we could say the candidate key would be these two columns. These two columns can tell you the value of every other column in the table. The candidate key is this one. We're in second normal form because there's no field that is functionally dependent on one of these. Can't say database tells us who the database teacher is because database tells us two different teachers. So we're in second normal form. And we are in third normal form because there's no transitivity. It's not that student and teacher tells us something which then tells us something else. So we're in third normal form. But we're not in Boyce-Codd normal form. And so what we would want to do is break the table down. We want to break the table down, and we could break it down several ways. Okay, so once again, I'm just writing the functional dependencies of the original table and reprinting the original table. We could break it down into a student-instructor table and then a student-course table. And the student and the instructor combined would have to be a candidate key. Whereas in this case, the student alone could tell you what the course is. And then we could also break it down into course instructor table and a student course table. We could also break it down into a course instructor and a student instructor table. Any of those breaking down would be considered a legitimate version of any one of these breakdowns, any one of these three breakdowns would then put this table into Boyce-Codd normal form. So as it is right now, it is in first, second, and third normal form, but it's not in Boyce-Codd normal form. Because this dependency, the teacher is dependent on the course, does not follow Boyce-Codd normal form. All right, so we said that Boyce-Codd normal form says if X tells you a field, then X must be a super key of the relationship. So if knowing the teacher can tell you the course, then the teacher must be a super key for the table, which is not true in this case. So this is not in Boyce-Codd normal form, so we can break it up. So the algorithm the algorithm for putting a table into Boyce-Codd normal form would be basically to go like this: to take all the relations all the tables in your relation, and then say, while there is a relationship in the set Q, or while there is a relationship in Q in the set D that is not in Boyce-Codd normal form, choose a relationship schema Q that is not in Boyce-Codd normal form. And if there's a dependency that X implies Y in Q that violates Boyce-Codd normal form, which would be, like example, the teacher tells you the course, that would be in violation of Boyce-Codd normal form. Then replace that with two schemas, Q minus Y and X union with Y. So what that would end up being would be Q minus Y. So for example, this field tells you this field. So what we'd have to do is replace it with instructor. We could have instructor and course, and then instructor and student, and that would be a way to break it down. So we'd have to take the set of X implies Y. We would take X and Y as one table, and then the last table would be the X minus the Y part. So it would be the X and the, sorry. We would have one table which is this field and this field. And then we'd have one table which is this field and all the remaining fields, which in this case would be the one other field. And the idea is to just keep doing this, keep applying this over and over until you break down your tables enough, so that you never have that violation of Boyce-Codd normal form, which is that one field can tell you another field, and that one field is not a superkey of the table. And obviously, as you keep breaking them down, you're not going to, if you have a table that follows second normal form, for example, and you break it down into two separate tables, the breakdown will definitely still follow second normal form. Same is true for third normal form and Boyce-Codd normal form. You'll never break it down and then all of a sudden a table that didn't violate any particular form now broken down starts to violate. That could never happen. So you just keep breaking the tables down until there's no more violation of whatever form you're interested in. So the point of these forms, it's not like, it's not like the database won't accept it if it's in one of these forms, and it's not necessarily bad to have a database that doesn't follow these forms. And obviously they get more restrictive. So it's first, second, third, Boyce-Codd normal form. Some authors will call it fourth, fifth, and sixth. They have like different versions of it. It's probably in your best interest to keep your data in, to have your data normalized. It would be best so that when you go doing queries, you don't generate records that were not intended to be in the relationships, and then they show up in your views and your SQL statements. Also, if a database administrator later on down the road decides to break a table into parts, if the original database wasn't in one of these strictly following forms, then you could also have that lossless join decomposition issue.